Welcome to Hot Chips 24. Session 5, Integration.
So the next couple of talks are going to be about integration in some interesting ways through stacking, et cetera. And we're going to start this off with a talk from Ron Dreslinski, who has, I was just teasing him, he has the first bio I've ever seen that would fit in a tweet. So it is a model of brevity that we could all learn from. Ron received his PhD in 2011 from the University of Michigan. He is currently a research faculty member at the University of Michigan with a research focus on low-power computing and interconnect techniques. So there you go. Have at it, Ron.
Hello? Okay, there we go. My talk today is on Centipede, a 64-core 3D stacked near-threshold system. This work really came out of a couple of research papers that we worked on a while back. So in 2006, we wrote a paper called Pico Server, looking at 3D stacked server-based systems and really where the performance was there. And in 2007, we started investigating near-threshold computing, so operating down at lower power levels. And these two techniques really combine well because near-threshold gives us a very low power solution, and then we're going to stack it on top of a 3D DRAM system where thermal constraints could be problematic. And so just to kind of motivate the problem, I've plotted up here a plot which gives the technology node across the bottom. The blue line is the supply voltage, the nominal supply voltage at each of the technology nodes, and then the green line represents the energy density within that system. And so the first thing to note is, around the 130 nanometer to 90 nanometer, our supply voltage has really stagnated. It's stopped decreasing at the rate we were used to. So we lost kind of that Dennard scaling effect where we were able to keep lowering our energy density. And as a result, the power, or the energy density on the chip is going up and up. And this leads to an emerging dilemma, which is you can put more and more gates on a die, but cooling and constraints limit how many of them can actually be turned on at a given time. Some people have referred to this as dark silicon, things like that. And so we started looking at what are the different operating regions people have talked about. Traditionally, we operate in the super threshold region. So I've plotted here two plots. On the top is energy per operation, and on the bottom is the delay of the system. And then I've scaled that across supply voltages. And so at the nominal voltage, you get a very short delay, so it's a very high frequency, but the energy per operation is very high. Now, this is typical of what you see in most commercial processors. You have to operate within some fixed TDP. You're talking about hundreds of watts, and the goal is we've been targeting kind of getting this high performance out of the system and not necessarily low power. Some of my colleagues at the University of Michigan started looking at subthreshold design. So taking this point, this operating point down, so the supply voltage of the system, down to this kind of energy minimum. So when the leakage energy is about equal to the dynamic energy, it creates this minimum. And at that point, you're saving about 12 to 16x in energy per operation, but it really slows down the system by an order of 500 to 1,000x. And so it's really great for sensors and embedded medical devices. And one of the devices that was built at the University of Michigan was this Phoenix 2 processor. And the idea here is it operates in the subthreshold region. You can see a picture of it on top of a penny there. It's very small. It's designed really to be a pressure sensor for in someone's eye. So it's great because it's low power. You can build some energy harvesting devices and stack those on top. But it doesn't really fit for a broader class of applications when you're talking about servers or general purpose computing. And so we said, well, let's not be so aggressive and back down where the delay is so large. What if we bring it back up a little bit? just above the threshold or in the near threshold region. Here we kind of get a nice trade-off in terms of energy per operation savings, but at not so big of a delay penalty. And so if you back it up a little bit, we're sacrificing about 2x of that energy savings we could get, but we're gaining back 50 to 100x of that loss we saw in delay. So now we're talking about a 6 to 8x improvement in energy per operation for only about a 10x loss in performance. And so then we're going to look at ways to kind of use 3D stacking and many core architectures to gain back some of that performance. One of the things we noted back in 2007 when we started looking at near threshold computing was the fact that the activity factor in caches, particularly L1s and then L2s, gets lower and lower. This means that the leakage component of those things in the system tend to dominate at a sooner point. So their optimal voltage where they're operating, so that minimum point in the curve, is actually higher for L2s than it is for L1s, and then it's higher than L1s than it is for cores. And so we went back and we looked at a bunch of different technology nodes and saw that this trend is continuing. And as we scaled it down into 32 nanometer, you can see on the right, I've plotted the actual frequency that's achieved at the kind of optimal energy point. And what you'll notice is that the core is running significantly slower than my L1s and L2s in the system. So this is really leveraging, we're going to leverage this for a new type of architecture. And so what a traditional many-core architecture looks like is a picture like this, where you have a core, it has an L1, there's some sort of interconnect, and then you go to the next level of memory. And the observation we made was that caches can operate at a higher frequency. So we're going to take that and we're going to introduce a cluster-based architecture. So the idea here is we're going to bring cores together and share the cache. And then we're going to operate them in 90 degrees. In this case, there's 4 cores, so 90 degrees out of phase. So we're going to clock each one of them at 90 degrees out of phase of the cache. The cache operates at 4 times the frequency. So this means each core sees a single cycle access to the cache, and all the coherence traffic happens internally. And so this provides a couple of benefits. The first is we have less coherence and snoop traffic. In the top picture, if one core's L1 needed data from another, it would have to go out onto the interconnect, perform whatever snooping operation, forward data back and forth over that interconnect. That consumes power and takes time. In the lower one, in the cluster-based architecture, cores that are in the same cluster can share data within their L1 cache without having to go out onto the network. Now, it does lead to some disadvantages. There's some core conflicts that can happen. So if I map together cores that have very aggressive cache behaviors, they could degrade each other's performance. So there's some things you have to watch out for. And then the second thing that happens is cores are traditionally tightly coupled with their L1 caches. They're really close together. That interface is built for speed so that you can get single cycle access latencies to your L1. And if we start breaking that apart and clustering them together and placing some muxing in there to determine which core is talking at each time, we end up with a longer interconnect. But we're gonna actually take care of that using the 3D stacking I'll show you in a minute. Okay. To improve performance when you need single thread performance. So this is traditionally you put out lots of multiple cores, but to overcome this kind of performance gap, but sometimes you end up with spots where you need single thread performance. We propose a boosting-based scheme. So we actually design these cluster-based approaches to operate nominally with all 4 cores running at 1/4 the frequency of a cache. And so we built this in a 130 nanometer design, and I'll show you some of the stuff as we come up, but here's some of the numbers that we came out with. We get 10 megahertz of performance at that point. If we need more performance, we can turn some of the cores in the cluster off, so we can make some thermal headroom. And then since the cache is already operating at 4 times the frequency of the core, we can boost up the core's frequency to match the cache. And so the cache doesn't change its voltage, the core bumps up its voltage and gets a little bit of performance. In actuality, I'll show you in a minute, we do some pipelining techniques to help get some better performance out of the system. So that's why the frequencies change a little bit there. And if that's still not enough performance, I can boost the system further, overdriving both the cache and the core to a higher voltage. Okay. To perform the cache timing, there's really 2 modes we're going to look at. One is when we're in this near threshold computing mode, when we have 3 or 4 cores in a cluster turned on. And the other mode is when we're in the boosted mode, when we have just 1 or 2 cores turned on. So when we're in near threshold mode, we're going to operate the cache in serial. So we're already operating the core at 1/4 of the frequency. So we have multiple cycles, cache cycles, to return the response. So that means I can pipeline my cache structure to do a tag access in the first cycle, do a comparison on the second cycle, and on the third cycle, only if there's a hit, access the data array. That saves energy because I'm only accessing the data array if I have a hit, and it's also pipelining the system to move forward. When I move to boosted mode, I no longer have as many cycles to complete my response, so I depipeline it. I do the tag and data array lookups in parallel, do my comparison, and return the data on the next cycle. What that looks like here is just a quick timing diagram that shows the cache access is in the green portion at the top, and you can see it does a tag, the compare, the read, and then it returns the data in time for the memory stage. When I move to the boosted mode, I extend out my tag and data and tag compare. So those are actually now, you can see the cache frequency is only half that of the core, but it still returns the data in time in the memory stage. So the system we actually built once we took this architecture is a 3D stack system. So we got the opportunity to kind of take those two original ideas, put them together, and build a system. This is the original design that we did. It's a 7-layer design. It consists of 4 layers that we designed at the top, and then 3 layers of DRAM, which was designed by Tezeron, which is a company that does 3D stacking. And I'll go into what's in here in a little bit of detail. So the Centipede, I guess it wasn't on there. So the Centipede system is 7 layers. 2 layers of it have actually come back from fab and have tested, and those layers include both face-to-face connections and through silicon vias. A face-to-face connection is where the top layer of metal is flipped on top of itself to make a connection, and through silicon vias is where we thin the wafer down so that it's 10 to 14 microns thick, and we access through the backside. And I'll show you some photos when we get to that spot. And we're expecting the full 7-layer version back sometime near the end of this year to test. So this is the system we actually have back and have measured, and I'm going to go through and highlight what each of these boxes are because it's probably very hard to read in the back. So up in the top, so you've got these kind of clusters. The yellow boxes are Cortex M3s, so they're actual ARM cores. We connect them together in clusters of 4, like I showed earlier, to an L1 cache. The L1 cache is made up of 1 kilobyte of instruction cache and 8 kilobytes of data cache. And then we operate each of the cores 90 degrees out of phase. This cluster consists of 1,591 face-to-face connections. So that's one cluster. And then we replicate that cluster out. In the full 7-layer version, there's 128 cores in the system, which is where we came up with the name Centipede, because there's 100 of them. In the system we tested, there's only 64. There's a bus system in the middle, so everything kind of communicates through this bus system. Each of the clusters connects on its layer to a bus hub in the middle, and then through silicon vias talk in the back-to-back plane to each of the layers up and down. And at the bottom of the bus system, it connects up to a memory controller, so actually it's 8 independent DDR-like interfaces. They're kind of a stripped-down version of a DDR interface. And each of those provides 128 bits to memory, and so there's 8 lanes of that. The DRAM system itself is 3D stacked. It consists of 1 layer that's a control layer. It was done at 130 nanometer CMOS, and then it has 1 gigabit of bit cells across 2 layers. And it provides, like I said, 8 interfaces of 128 bits in a DDR2-like interface. One of the interesting things in the architecture we brought from PicoServer is that because the DRAM is so close in the 3D stack system and the cores are running at such a low frequency, the access time on a closed page in memory is only 15 cycles from an L1 miss. So at that point, it doesn't make sense to necessarily have an L2 there to hide that latency. And so we've removed the L2s in the system to kind of give us more room for computation to exist. So this is a list of the total number of TSVs and face-to-face connections. So TSVs are where there's back-to-back kind of connected together, and face-to-face connections are where we flip the two together. In total, the system has quite a few. I don't remember the total number. So again, back to here, the whole system was designed in a 130 nanometer process. The layers that we designed were 12.66 by 5 millimeters each. There were 28.4 million devices on the core layer and 18 million on the device layer, When you multiply that out by our 4 layers, it comes out to just short of 100 million devices on the chip. The 2 layer that we actually got back looks like this. We got a cache layer. They took and flipped the core layer on top of it and connected their top levels of metal. Then they thinned the core layer down, exposing the TSVs, the back-to-back TSVs. And rather than stacking it on the DRAM, they've just put aluminum wire bond pads down that we've bonded to so that we can measure the system. And so we've tested both the face-to-face connections and the through-silicon via connections. And the thickness, when we slice the wafer in half, the thickness of that core layer is actually only 12 microns thick, so it's very thin once they've thinned it. So the connections between the cache and the core, so I'll zoom in a little bit. This is our cache in the system. We had to custom design our own SRAMs. This was done for 2 reasons. First, we want to operate at near threshold, so we wanted a more robust SRAM cell, so we didn't have as many issues with variability. And second, the process requires a minimum TSV density. A TSV needs to be placed every so often in the system, and if you took a standard, just artisan memory that compiled out and tried to place it down, the smallest one available just fit within the minimum TSV density. So you couldn't make anything bigger than the smallest array they had possible. So we wanted to get a little bit better yield out of the SRAM, so we went and designed our own. The block is made up of a bunch of different SRAMs that make up the different ways of the cache. The kind of perimeter filling it in is the cache controller and the sea of gates. The little dots that are there are the physical connections between the cache layer up to the core layer. So that's where the cache, so this is one cache and it's going to connect to 4 cores. And I'm going to show you the core layer in 1 second, and you'll notice that the dots stay in the same place. So there's the cores. So the 4 cores are sitting on top of the caches and communicate down. So this really helps with the fact that when we went to this cluster-based architecture, we split out the caches, but now that we've folded it underneath and done it in 3D, we can bring back that close interface that allows the core to talk in a short period to the cache cycle. In fact, if you kind of split this and look at the TSVs going through, for one cluster, there was 1,500 face-to-face connections, and we went back and rerouted the system without 3D, and we saved about 600 to 1,000 microns in routing for each one of those wires. So it also helped us in some congestion around the SRAM arrays. So that's really where we use some of the 3D stacking to help us. The silicon results, so this is the system we actually tested, just highlighting it again. I'll walk through a couple of die photographs. So this is the actual die that we got back. The stats on the bottom are the same as I mentioned before. I'm going to highlight a few things first. The first is that we're looking through the back side of the core layer. So traditionally, you look at a die photo, and you're looking down from the top layers of metal into the chip. So you can kind of see like some different colors as you hit the different metallization layers. In this case, we've actually taken 2 chips, stacked them on top of each other, and thinned 1 wafer down. So what we're really staring at is through the very thin wafer, through the back side of the silicon, looking at what's going on inside. So we're looking through the back of the core layer. And so the centerpieces, well, I guess I didn't get that part. You can kind of see the outline of the 4-core cluster there, and then we've replicated that around the system until we get to 64 cores. Here's the DRAM interface and the bus hub that was kind of the central part of the system that communicates up and down. And that's where you can kind of see the TSVs have been ground down to where they've been exposed. And then we've taken and placed aluminum along the pads on the sides so we can actually talk to everything in the system. And that's where the TSVs come out on the side. So we evaluated the system looking at 4 different configurations. One where we have 4 cores turned on per cluster. In that case, you can see that the cache is running at 160 megahertz and the cores are running at 40 megahertz. Oh, no, the cache is running at 40 megahertz and the cores are each running at 10 megahertz. As we boost up to 2-core mode, the cache gets up to 80 megahertz and the cores are at 40 megahertz. And then when we bump down into the bottom right corner, the 1-core mode, we actually have to overdrive the bus system to sustain the latencies we're used to. At that point, the cache is running at 160 megahertz and the cores are at 80 megahertz. Now, these numbers seem relatively low, but again, this is running in a 130 nanometer process. And that was because that was what was available from Tezeron, the group that did the 3D stacking. Because from 130 to 90 nanometer, they changed the wafer size, so they weren't able to handle the wafers going forward. So measured results in the system, I've plotted here for each of the different core configurations, 4-core, 3-core, 2-core, and 1-core. The big difference between 2-core and 1-core is that when I jump that final boost, I really had to up the bus frequency in the system, and the bus system started consuming quite a bit of power, and so did the cache as I depipelined the cache and raised its power. If you want to look at it in terms of what does a one-core cluster get you, the performance out of one core is the same as 15 four-core clusters. I think those are the power, same as 15. Really, the idea here is, and I'm going to get into it in a second, is trying to evaluate the amount of energy efficiency in the system. And so when we need single-thread performance, we can sacrifice kind of this power and bump it up and get it, but most of the time we want to run in this four-core mode. And so if you look at the performance that comes out of the system, so this is measured in DMIPS. So the four-core system gets 1,000 DMIPS, or the one-core system does, and the four-core system gets 12.5. So if you plot that in DMIPS per watt, you can see for energy efficiency in four-core mode, we're getting around 3,930 DMIPS per watt. If you scale all the way out to the one-core mode, we're only getting 860 DMIPS per watt, but we got a peak of 1,000 DMIPS. So if you need performance, you pick out on that side. Those were the measured results at 130 nanometer. Just to kind of compare it to some industry specs that are out there, the ARM A9 in 40 nanometer gets about 80,000 DMIPS per watt. And if we extrapolate out the Centipede design down to 45 nanometer, it comes out at about 18,500 DMIPS per watt. And so just kind of concluding the talk, near threshold computing really offers us an opportunity to bring the power consumption down on processors. So we can find ways to meet TDP. It's really beneficial when you're looking at a 3D stack system where you're more concerned with thermal constraints, particularly if you're going to stack it on top of DRAM. You want something that's low power. Near threshold computing gets about a 10x energy efficiency improvement, but it does so at a 10x loss in frequency, so you need to use a parallelism to kind of overcome that and achieve performance. And it's kind of that spot where you're trying to trade off the balance of performance and energy. And so we also design a system that allows us to boost single thread performance to help overcome Amdahl style bottlenecks, serial portions of code or locks that are critical locks that are being held. We also demonstrated a large scale 3D CMP design. It has 64 cores in the one we currently tested. The one that we're expecting back at the end of the year has 128 cores and will be integrated with DRAM. And as part of this, we kind of showed that 3D designs were feasible. Thank you.
All right, so we have time for questions. You can come to the microphone so everyone can hear you and give name and affiliation. That would be great.
Satoshi Matsushita, NEC. Looking at the figure on the page 29, the distribution of power, the power consumed in the core looks smaller than the power consumed in cache and memory. But do you have any idea to reduce the cache and memory power? Otherwise, I don't think that it's useful to reduce the core power using the quite low voltage in the core.
Right, so the problem we're having with the technology was really the leakage power. If the caches are that size and are not being accessed, there's not much I can do to reduce the power besides looking at drowsy cache techniques or making the cache smaller, other techniques to reduce its power. It's actually a little bit, we could reduce the cache power, but then we wouldn't be able to pipeline across the cores either. So it's kind of this balance, and if you look back to our original study in 2007, we kind of did a performance sweep of number of cores, number of caches. It was in ISLPED, so that's kind of breaks down how we ended up at this kind of ratio between core to cache.
How much is the cache size right now?
Right now we have 1K of iCache and 8 kilobytes of Dcache per cluster. So it's on the small side, but we were trying to get a lot of cores into the design. Full system, we'd expect those numbers to be a little bit larger.
Thank you.
Hi, Greg Roll, Intel Corporation. Did you use any special I/O circuitry between the stacked layers, or was it standard CMOS inverters?
There were some. There's two different layers that happen. There's a set that's kind of
Certainly driving the DRAM would need the.
Yeah.
the
So the
analog,
stuff
right?
going to DRAM needs ESD protection and stuff when we stack, because it's actually a die to wafer bond. The other bonds are wafer to wafer, and we didn't need any extra protection on there. We did use duplicate TSVs in certain spots for critical lines that we weren't sure if we'd get a connection or not, so we wanted to make sure that there was enough signal there.
And has your research investigated any of the yield issues with die-stacking, or are you just proving feasibility at this point?
We were just trying to prove feasibility. From our system, we got back and tested 17 chips, and they had, I can't remember the number that was on there, quite a few TSVs, and we didn't see any failures. But we didn't have enough to really do a full yield analysis on anything.
Thank you.
John Massey, TechVisor. So, you know, we don't see as many interesting chips from universities as I'd love to see, right? Talk about how many people worked on this, how long did it take you, what sort of tools did you use? You know, sort of tell us a few things about what it's like to do this in a university these days.
Okay, so I think it's difficult to tape out chips at a university. We have some interesting things happening at Michigan that are helping us out. We have a great research collaboration with ARM, which gives us access to RTL and their cores, so we can actually get access to the M3, build it, tape it out, see how it works. Between myself, Trevor Mudge, who was my advisor, David Blau, and Dennis Sylvester, there's an enormous number of chips that we tape out every year. So we've got a pipeline of students who understand what needs to be done. For this particular design, we started kind of early investigation when we put the proposal together and kind of defined the architecture for about a year. And then we had about 2.5 months from the time we actually got the standard cell libraries and everything from Tezeron telling us what the TSV pitches were, minimum density requirements, to actually finish. And the design team for the first month was, I think, 4 of us. And then as we were taping out and finishing out, there were about 15 students involved. So we picked up quite a bit of manpower at the end to kind of push us through the LVS, DRC, last level checks, get scripts to test the 3D stacking and everything.
So we have time for one more question if there are any. All right, with that, thank you very much. All right, so the next speaker is Ephrem Wu with Xilinx, and unfortunately his bio does not fit into sadly does not fit into a tweet. So I actually have to kind of pull it out. So Ephrem is a senior director of advanced communication at Xilinx. He's responsible for advanced FPGA solutions for wireline and wireless communications infrastructure. He joined Xilinx in 2010 and led the design of the industry's first heterogeneous FPGA. From 2000 to 2010, Ephrem was with Velio Communications and LSI, which acquired Velio in 2004, and was responsible for leading the definition and development of packet switches and network processors. Prior to that, he held various ASIC circuit and software design positions at SGI, Hewlett-Packard, Panasonic, and AT&T. One of the classic, tech vagabonds, I guess, that lots of us are. Here's Ephrem.
Thank you, Don. Good evening. Thank you for having me here. Suresh and I co-authored these slides. Obviously, a lot more people were involved in a project like this. And on behalf of the Vertex 7 HDDM, I'm going to present the world's first stacked FPGA, and it's my pleasure to be here. So I would like to first outline one key application for a product like this Vertex 7 HT, and then I'll go through the kind or the variations or the combinations of products we can build with just 2 distinct dies. Then I will go through the packaging, especially between layers, what interconnections are there. And then at the end, I will specifically focus on 2 types of interconnects within the package of this type of product. First, I'd like to show you a very typical application for this type of FPGA. What I have here is a two-dimensional view of a communication chassis. The box, the green box on the left, represents a communications line card. The orange box on the right, or in the middle here, represents the backplane connector, and then the gray box represents a switch fabric card. So this FPGA, one key application for this FPGA is to serve as a bridge between the optics and the rest of the line card. So if you look at the black box there, that's the FPGA. That's a 3D stacked FPGA. On the left-hand side, we have the so-called line-side interface. On the right-hand side, we have what's called the system-side interface. The line-side interface connects to optical modules. And in this particular example, I'm showing 4 100 gig optical modules. Each optical module can be, for example, a next generation CFP2 or CFP4 optical module. This optical module has an electrical interface that has 4 differential pairs, each pair running up to 28 gigabits per second. 4 by 25 gig is nominally 100 gig. The extra bandwidth is there for error correction. This is for error correction on the line, not on the electrical side. So this FPGA has 16 28 gig SerDes packed into one chip. These 16 28 gig SerDes are also called the GTZ transceivers. So with 16 GTZ transceivers, the Virtex 7 HT can connect to 4 100 gig modules. And that's why I'm calling this a 400 gig line card, specifically a 4 by 100 gig line card. On the right-hand side of this FPGA is the system side interface represented by the yellow double arrow. The system side connects to the rest of the line card. These transceivers run at a slower rate. They don't run at 28 gig. They run at up to 13.1 gig. These transceivers are also called the GTH transceivers. The main difference between these two transceivers, the GTZ transceivers and the GTH transceivers, is that the GTH transceivers can drive longer distances, but at a lower line rate. In particular, the GTH transceivers are actually backplane transceivers. They're capable of driving 2 connectors with 1 meter of PCB trace in the middle. So what I've shown here isn't even using the full capability of the GTH transceivers. This is what's called a chip-to-chip interconnect, where the channel has at most 1 connector and maybe up to 20 inches or so of PCB traces. So with 16 28 gig transceivers and up to 72 13.1 gig transceivers, this FPGA has a total receiver bandwidth of 1.4 terabits per second, and the same, 1.4 terabits per second of bandwidth for the serial transmitters. Now let's take a look at what's inside this FPGA. We have 2 distinct dies here. One is the red die that represents the GTC IC. There are altogether 8 28 gig transceivers in this die. The black rectangle is the FPGA, and the GTH transceivers are also there. Why do we do it this way? Why do we use stacking to build this product? We have optimized the FPGA for low power and for enough performance. We work with our foundry partner to optimize the IC process. The 28 gig transceivers require a little bit more performance from the process side. So instead of having a high leakage process for the FPGA as well, we opt for a high performance process for the GTZ and a high enough performance but very low power process for the FPGA. So as you can see, by combining these 2 dies, we can now have different combinations of products. We can mix different numbers of transceivers and FPGA resources. And by FPGA resources, I mean the usual LUTs or the CLBs, configurable logic blocks, block RAMs, and they're also called BRAMs, DSP tiles, and so on and so forth. So the family member on the left has one GTZ IC and one FPGA. So this product has 8 28 gig transceivers and 24 GTH transceivers. The one in the middle is the one that I'll show you in more depth today. In fact, I have the actual sample in my pocket right now. I can share that with you later if you're curious. This product has one GTZ IC, so that's 8 28 gig transceivers, and 2 FPGAs. And so that also, these 2 FPGAs also come along with 24 times 2 or 48 GTH transceivers. And the biggest one is the one on the right. It has up to 16 28 gig transceivers all packed into one package and 3 FPGAs. The one on the right basically maxes out the interposer maximum dimensions. So that's pretty much the biggest one that we can build, at least with today's technology. So I took a couple pictures of the product without the package lid. You see here, the green part is the ceramic package substrate with all the chip caps around it. And then you can see the 3 different dies, 2 FPGAs, and 1 GTZ IC. You don't see any wiring because you're looking at the backside of the silicon. It's all smooth like a mirror. You do see a little bit of colors down below. You're actually seeing some of the exposed interposer. So let's take away the 3 dies. And now we see the passive silicon interposer underneath. For a designer, a designer can really think of it as extra layers of metal that join multiple chips together. That's one way to look at it. And I've angled the light for this picture so that you can see the die-to-die interconnects showing up as these orange vertical lines. Here's a cross-sectional view of the 580T product. Starting from the top, we have 3 different ICs. 2 of them are identical, 2 are FPGA slices, and the red block represents the GTZ IC. They are interconnected by wires drawn inside the interposer. And on each end, on each wire, is a microbump represented by the white circle. The passive silicon interposer contains TSV, so for signals that need to go out of the package or signals that come in from the package or power and ground, for example, they would go through the C4 bumps. From this point on, it's pretty much the same as a traditional flip chip design. Note that this picture is not drawn to scale. The micro bump pitch is actually about 1/4 of the C4 bump pitch. So the areal density is 1/16, or 1/16 I should say 16x the areal density of the C4 bumps. The 2 types of interconnects that I'd like to focus on in this talk are what I call just type 1 and type 2 interconnects. When we talk about interconnects, people often kind of, they often think about TSVs right away, but there's only a small fraction of these signals that go through TSVs, and those are the so-called type 1 interconnects. They go between the top die and the package BGA balls. We typically have to associate multiple micro bumps with 1 C4 bump for reliability reasons. So we would connect multiple C4 bumps to a TSV. For the type 2 signals, they never leave the package. They're always within the package. They let 2 dies, or maybe even more than 2 dies, to talk together within the interposer. The interposer in this case is kind of like a very thin, very fine-pitched PCB. So with these signals, we only use 2 micro bumps, 1 on each end. Before I go deeper into these interconnects, I'd like to digress a little bit and talk about the manufacturing flow. This is very important. Xilinx has spent about 7 years working on the stack silicon research and development and nurturing the ecosystem and working with our partners. Xilinx designs the top dies, the interposer, and the package. And we have partners to help us to supply the silicon, the package substrate, and to assemble the final product. And Xilinx, in the end, tests the final product. And we have made the wafer sort vectors such that they're portable to final test. And obviously, at final test, we have to also test connectivity between every pair of dies. So now let's take a look at the Type 1 interconnects. The most challenging Type 1 interconnects are the 28 gig serial signals. Here I'm showing you the transmitter signal. This is a simulation. So we basically pass a PRBS signal into the simulator, and we observe the final eye diagram, which is a composite of many, many cycles of transitions. What you want to see in this kind of diagram is, of course, a very nice big eye. What I haven't shown you here is that we actually had to build a very detailed channel because we couldn't find one out there when we started the project. This channel consisted of an end-to-end channel for signal integrity simulation, starting from the top die through the TSVs, through the substrate, through the board, and back to the same chip. So we assume that both ends of the channel have a device that have TSVs in there. So we would think that that should be the worst case. But it turns out that these TSVs don't really harm the signal integrity. You might have seen that at the tutorial yesterday. So this is a simulated transmitter eye at 28 gigabits per second. And this is the actual measured transmitter eye from a scope. Now let's go to the Type 2 interconnects. So what I have here is a cartoon showing two dies in 3 dimensions. And I'm going to call this type of layout microstrip layout with side shield. And the pictures will explain what that means very soon. So this is sort of a flip chip design. So we have the micro bump pads at the bottom of both pieces of silicon. The micro bumps will join these micro bump pads with those on the interposer. And here's the interposer. And now I'm showing a dotted line there, and that represents either a clock signal, either a clock or a signal. Here's the cross-section of the wires going across these two dies. We have a pretty conservative approach here. First of all, there are 3 metal layers available to us. We reserve the middle layer for a ground reference. Most of it is basically used for ground reference. We developed our own models for these wires. Some of these wires are pretty long, and I'll show you the length later, or length distribution later. In practice, every signal is shielded with a ground wire. So basically, metal 1 and metal 3 do the bulk of the job carrying signals across these two dies inside the interposer. Here's a distribution of wire lengths across this interface, and I have a very technical term for all the FPGA resources that are talking to this 28 gig GTZ IC, and that technical term is called beachfront. So all the resources, CLBs, interconnects, you name it, that talk to the GTZ IC are known as beachfront property. So the reason we do that is that the users will never see this wire length distribution. We basically hide that from our users. When they close timing with respect to our beachfront property. They don't have to worry about the stuff that we already worried about. So you can see that the median wire length is somewhere between 2,500 to 3,000 microns, so less than 3 millimeters. And obviously, we keep all the critical data path signals as short as possible. The tail is rather long. There's some pretty long wires here, but those are basically practically static signals. I might have alluded to this earlier, that we built our own model. In particular, this is a RLC model. We included inductance in this model. And we have enough return paths here built into this interface. So our goal, when we started out making this device, our goal was to be able to use our existing static timing analysis methodology to verify the timing behavior between the GTZ IC and the FPGA. So how do we do that? The tools really were not mature enough to support that kind of flow yet. Certainly the tools didn't understand RLC, and certainly our SPICE simulation told us that we should worry about inductance as well. But by drawing the layout this way, some may argue that it's a little too conservative, but it works. We can safely ignore the inductive effect on this interface. And we calibrated our STA timing results with SPICE for a number of wires with different wire lengths. And because the layout is done in a regular manner, we were able to apply this across the entire interface. You probably remember from the chart earlier that there are actually 4,138 wires across this interface. So having an automatic approach, an STA approach, will certainly help productivity. Because for sure, we don't run this kind of analysis once, right? You'll probably have to run it multiple times when something changes. So we were able to achieve this result, the kind of productivity and kind of quality that we would like, by having a mix of layout style that's really borrowed from the PCB people when you think about it, and also careful calibration of what's essentially an RC-based timing tool to SPICE. So in summary, I've shown you the industry's first heterogeneous 3D FPGA. And I've shown you how we can mix and match one FPGA slice and one analog ASIC to create a scalable product family. I've reviewed our stacked silicon supply chain, and I've also shown the quality of the 28 gig signals over TSVs. Although we lacked 3D timing tools for the die-to-die interconnects, with a mix of careful calibration, SPICE simulation, and STA, we're able to have a productive methodology in the end. That's all I have. Thank you.
So before we take questions, and we have time for plenty of questions, a couple of announcements. The food won't be served until 6:50. And so we're going to end well before then. But if you go out to the side, there'll be liquid refreshment for those of you who want to get a glass of wine and use that as a way to unwind. So when we're done here, you head out to the side, get a glass of wine, and then don't run over to get the food because it won't be ready yet. The other thing is, remember that the nighttime keynote starts at 8:05. So get back here by about 8. And the program, it says 8:55, whatever. It's 8 o'clock, really. Just come back by 8. And with that, we'll actually start with questions first over here.
Ron Nicholson, Hot Paw. How does the dielectric of the interposer compare to the dielectric of the top layer of the metal on the main die? And does that allow opportunities for putting long wires within a die on the interposer?
Yeah, like I said earlier, in a sense, in a way, you can think of the interposer as extra layers of metal. I don't remember the specifics in terms of dielectric and whatnot, but you can really just think of it that way. Thank you.
All right.
Hello, Ephrem. I'm Ted Williams at Microsoft Silicon.
Hey, Ted.
My question is for you to explain the manufacturing test strategy, and in particular, do you have the strategy that the die that you're mounting on the silicon interposer are known good die at that time of the mounting, or do you throw away the whole assembly if there's a defect in any of the 5 die that might be on top of the interposer?
Oh, yes, absolutely. We ensure that we have a wafer sort program that will give us known good dies ahead of time.
But how are you able to test it with the microbumps?
Oh, okay. So the final test is an extra test set of tests, right? Just for the die-to-die interconnects, and that's a very small portion of our design. But the bulk of the design would have to be, proven good at wafer sort, and we actually port these wafer sort vectors directly to final test. So there's a very small fraction of vectors that are just targeted for die-to-die interconnects at final test.
So your ATE can connect to all the microbumps?
ATE, final test, right? Package test, yes.
No, before packaging, before the interposer.
No, we don't do that. It is possible, but we don't do that.
Okay, I'll talk to you later.
Yeah, we can talk offline.
Satoshi Matsushita, NEC. What is the signal level of the Type 2
Oh,
interconnect?
good question. I forgot to mention that. They are just regular CMOS signals.
Okay, and how much is the driver and the driving power for the Type 2 signal?
Yes, so that's a very good question. It depends on the wire length, and we definitely need to be very careful on the transition time, because as I said earlier, there's some inductive effects in these wires. In fact, this kind of design is somewhere between a PCB and regular silicon wires.
Do you use a single level drivers for the Type 2, or the changing the driving force according to the length of the Type 2 connections?
You mean like a level shifter? Or?
No. The driving force, driving current.
Oh, yes. I mean, we use SPICE to make sure that we have the right amount of drive and the receiver is sensitive enough to pick up the signals. Again, we have to make sure that we control the slew rate so it doesn't get too sharp or it doesn't get too slow. Yeah,
my question is that do you use a uniform driving current for all the Type 2 signals? Or?
Yeah, pretty much,
okay.
Yeah.
Okay, we'll take a question over on this side now.
Yeah.
Bob Masley, Oracle. At wafer test, do you probe some of your microbumps or all of them?
You're not talking about between 2 dies, right?
When you're testing the die before assembly.
So we don't touch the microbumps.
How do you do test if you don't touch the microbumps?
You can have a sacrificial pad.
Thank you.
So Albert from Altera. My question is for the 400 gig application, what's the range of power consumption? I mean, worst case power for customers.
Oh, okay. So that's a factor of many, many things, right? So you can go look into our data book. But I think I don't remember the precise numbers for the SerDes, but I think it's comparable to what Xilinx has been making.
So do you have a number, like a ballpark number?
Ballpark number, I think a couple 100, 300 milliwatts, something like that.
I mean, total, for the whole die, for the whole application.
Oh, for the whole application. I have so many different variables here. It's
okay.
So could be, tens of watts. It could be a lot more than that.
Any further questions? Okay, with that, let's give Ephrem a hand. That was a good talk.